So we'll move quickly on. Dr. Frank Effenberger is going to go into a lot more detail on the options and the coexistence and the migration opportunities.
Okay, thank you very much. So my talk is talking about how to manage this life cycle of PON. So we've developed PON technology over many years. Really, my entire career has been devoted to this technology, and it's very rewarding to see that it is expanded to the extent that it has. But the nice story is that we have different technologies, one after the other. It'll grow, it'll become mature, and it will then decline and be replaced by the next technology. And it's an ongoing process here of renewal, all of which is important that the fiber plant, which is the most expensive part, stays the same, and you're kind of reusing that big investment again and again. So that's a big business success story, and we've managed that now through a couple of generations at least, and now we're looking at how to extend it even further. And indeed, this GPON to 10 GPON to 50 GPON is sort of the trajectory that a large part of the world's PON infrastructure is going through. And in fact, the 50 GPON is also a point where EPON and GPON deployments, mainly in Asia, are starting to get converged into a single system. So we're sort of saying when we always had a sort of a split market, it's starting to become more converged. And so actually, if we look at the actual real story here, the PON evolution is a little more complex. So actually, there were a lot of, the prehistory of PON. So there were 50 megabit, 155 megabit, 600 megabit PONs. The 600 megabit, the BPON, actually got about 5 million lines deployed until it was superseded. Then GPON is really the big hit. That's maybe 800 million lines over the entire world. At the same time of GPON, there was EPON. So the Ethernet folks wanted to get involved in this fun new PON world. That's expanded, but not to the same extent. And it's very regional based. So basically in China and in Japan, you'll find the largest deployments of EPON networks. And then after that, there was the 10 gigabit generation, both ITU, XGPON, and 10G EPON came on. And then there is this convergence to 50G. There's also the TWDM PON, that's the things in the sort of purple shade there. Multiple wavelengths, so to get to even higher capacities. That is not really, at least for 10G systems, that's not been very successful. Maybe for multiple wavelengths of 50G might be the sweet spot where that technology starts to make sense. Because at some point we're going to have to go to multiple wavelengths. I think we've seen that in many networks in different application spaces. It's just what speed is that point where you finally have to do that. And then in the distant future, there's very high-speed PON, so that's something like 250 gigabits per second. And it's kind of hard to imagine what world we live in where we need that much bandwidth going to people's homes, but we've also learned never say that so much memory is enough for your computer and so on. So going on to sort of the key issue here, which is managing coexistence. So no matter where you jump, or wherever you start on this tree of PON, you need to have to move from one point to another. You have to jump to another branch. And what coexistence means is that you don't have to let go of the previous branch before you grab onto the new branch, right? So that makes sense. And so there's several different ways that you can try to implement this. One is to use separate PONs sharing a common cable infrastructure. So really the PONs electronically are separate, but they are sharing cables and duct and all of that. You can have separate OLTs sharing a common PON. So here it's actually becoming more close together. They're actually traveling over the same glass, but they are separate equipments. And then there's even the multi-PON module concept where you actually have a single module that drives multiple PON technologies down into a common ODN network. And so each of these has sort of advantages and disadvantages that we'll go over. So the first one is the common infrastructure. So here you see we have two different flavors of PON here. There could be generations. So there's the blue PON, And that's connected to certain fibers, goes and lights up certain splitters. Those are so the blue PON splitters. And you would connect your blue customers to those splitter ports. And then you'd have a red PON that will be running over separate fibers. You'd have separate splitters out in the field, and then you'd be able to connect those ONUs to those fibers. And the systems here are totally separate, which is that's an advantage. It's more flexibility. They don't have anything to do with each other. No coexistence features is required. And actually, this is the system that Verizon used to manage the coexistence of BPON and GPON, because both of those systems use the same wavelength plan. So you have to do this. There's no other choice. They would conflict if you went on the same fiber. Another interesting aspect here is it also can reduce the initial capex that you require, because the out of the splitter it's connectorized. You can groom all of your customers onto a fewer number of splitters. So when you just start to deploy the red PON, say the red PON is the new system in this setting, you could light up just a single splitter and start to move customers over to that splitter as you need to. And then only once the takeoff, the take-up starts to really start moving, then you can light up more splitters and manage it that way. So it has some advantages. It also has disadvantages that pretty much requires connectorized outside plane. So you're going to have to be able to do manual rearrangements of the fibers here. So that's something that some operators are not so eager about. Although I think it's sort of become more of a commonplace design principle. Accurate and accessible records are very important here, because now that fiber patch panel that's out in the splitter cabinet, that's everything. You have to know where all the fibers are. You have to make sure the fibers are properly labeled, or otherwise you can tell what you're doing when the craftsperson plugs in the fiber. And then also there's no synergy between the systems. So because they're basically just two separate systems, you can't do anything interesting like you actually deploy two different PONs to the same customer, and then you could do something like protection in that regard. So the common PON, this is sort of a very common kind of architecture that's been the focus of a lot of standardization, to try to have the PONs, have the different PON technologies share the same glass. So you have two different OLTs, same as before. You use a coexistence element, which is basically an optical filter. It takes the different wavelengths of the different systems and merges them together onto a single fiber. And then now that leads out to your splitters. Those are now, you can see, are purple because they're supporting both the blue and the red system. And now you just plug the ONUs into these common splitters. So this has the advantage that you have separate OLT equipment. So if you have your working OLT and it's working just fine, you don't want to mess with it, you don't have to. You just put a second OLT next to it and take all the combination optically. No outside plant rearrangement work is really necessary. You do have to go out to the customer's house to change his ONU, because typically that's new equipment. That the optics are built into that typically, as well as like the UNI, the actual interface you're giving to the customer is probably going to have to be upgraded also, because you're increasing the bandwidth. So you're going to have to change the equipment there anyway. The sort of challenges here is that while the PON systems have to be coexistent, they have to have the wavelength plans arranged so they don't conflict, right? Generally, you need to overlay a new network over the entire access of your whole system, because as you say you introduce this new PON system, all the new customers are not going to be neatly organized onto one splitter. They're going to be scattered all over the place. And so you basically have to light up the new PON system all on day one in order to be able to then sell that service and be able to offer it to people on a quick basis. And then last but not least, there's multiple OLT chassis, which that was sort of an advantage, but it's also a disadvantage, size, weight, and power. There are some situations where the central office or maybe a remote cabinet maybe just doesn't have enough space for that kind of extra equipment, right? So that's an issue to think about. And so that actually is what led to this third option, which is the multi-PON modules. And so here, the OLT optical modules, typically SFP, integrates 2 or even 3 PONs into a single SFP module, right? And so now you only need a single OLT chassis, but it's implementing the same wavelength-based coexistence. So you're lighting a single set of splitters. You can connect all the different ONUs to those, and they pick off the wavelengths that they want to use. So very neat in a sense. Of course, the same challenges there. PON systems have to be coexistent. Generally, you need to replace all the OLT modules to activate this new system. And the chassis has to have a sufficient bandwidth capacity. So you can imagine if you have a chassis that was designed with GPON in mind, it's going to have a certain backplane capacity. If it needs to support XGPON, it's going to have at least 4 times more capacity in order to have a similar kind of service profile. So there's issues there. The chassis is not just a magic thing that takes care of itself. One thing to point out here is this multi-generational coexistence modules. The optics designers continue to amaze. It was always neat that they could manage to stick a single PON into an SFP module, and now here they've managed to stick 3 different PONs, so GPON, XGPON, and 50G-PON all inside the same module. And this is being trialed. This was actually Visa from last year, and now in this year it's moving towards full first office application type of deployments in Asia. So 50G is moving, and MPM happens to be the technology that they prefer in their networks. So that means that wavelength plans are very important for coexistence, because it's really it's the lifeblood of them. So if we look at the different generations, sort of these colored boxes around the PON systems show kind of what the wavelength plans are being used. So GPON and EPON, for example, they all use the same 1310 and 1490 nanometers. XGPON and 10G-EPON, they both use the same similar wavelengths, 1270 and 1577. And then so the 25 and 50 GPONs sort of use a similar, although slightly different wavelengths there, but you can kind of consider them as sort of in a group of coexistence. So in any one of these groups, you can deploy one, but possibly not the other, unless you do some kind of engineering about it. And then there's the NG-PON2 or TWDM PON systems. Those are all C and L band. Those can coexist with almost anything because they're quite flexible in a sense. And then VHSP, that project is just getting started now. There's hopes to be a sort of a first version of a white paper that's going to talk about it. Actually a supplement, but basically it's just sort of the beginning start of that analysis. But it might be in the O band, it might be in the E band, might be in the C band. We don't really know yet. It depends a lot about technology choices that haven't been made yet. So how much of this coexistence can we stand? Or more importantly, how much can we afford? Because that's usually what it comes down to. So when we first started to ask this question in 2018, 2-generation coexistence was kind of what a lot of people were centered on. It enabled low-cost optics. You know, it's because we don't have to share so many, we have a limited amount of wavelength resources. We can't, support so many systems was the concept. And so we try to make do with 2 generations. But later, as deployment of 50G technologies approached, 3-generation coexistence became really the de facto requirement there. And part of that is that the cost, benefit of the 2-generation coexistence kind of went away. It seemed like it's not so much added cost to support 3 generations. And then also a big recognition that access systems have a really long lifetime. Once you've deployed something, it's out there for a long time. Probably you will retire before that system goes away. It's the way you can think about it. So it's like a 30-year life cycle. Because typically equipment is usually warranted for like 20-year life, right? And it takes some years to get it deployed. So 30 years is quite plausible. And so if you look at that, at any point in time, you deploy 1 generation, then you deploy a 2nd generation on top of that, and it's overlapping. Then a 3rd generation comes along. The 1st generation still isn't gone yet. It's going to slowly tail away. So you really need to have 3 generations, and that seems to be kind of the design principle that we're working on, at least in the standards community right now. So to summarize, optical access is a gift that keeps on giving, and that was really the whole point. The whole, sort of the motto is fiber is final. Once you put the fiber out, you should never have to go deploy that outside plant again. The optical electronics, of course, will be renewed over time, and that's what this handling the coexistence is really all about. And so this rollout of new technology really has to be done with some forethought. You want to avoid forced replacements that waste money unnecessarily. It disturbs customers that don't want the new service. You shouldn't force people to actually change their equipment. Outside plant rearrangement might be involved, so you have to consider being able to do that. OLT, replacement or reinforcement, is sometimes a factor, so you should think about that. Replacement of ONUs that have to be upgraded, that is a thing, so you're going to have a system and a solution for that. And then the services that all those customers need to be migrated. So when you change someone from a GPON to an ex-GPON equipment, you have to have the back-end systems that migrate all of their services, so their phone number, if they're doing voice, all of their internet access, all that stuff has to be migrated to the new system that they're working on. So that's important. And then, so 3-generation coexistence appears to be the current trend, and it seems to be, will be able to be maintained for the foreseeable future, maybe this generation and the generation beyond. So, thank you.
Brilliant. Thank you, Frank.